Hi everyone, I am Shruti Pandey from Chemical Engineering Department of IIT Kanpur and I welcome you to the third lecture of the chapter Haloalkanes and Haloarenes in Chemistry of Class 12. So in the previous lecture, we discussed about the nature of the carbon-halogen bond that was related to the electronegativity property, that the carbon-halogen bond is always polarized because of the separation of charges. And then we also discussed about the bond length of the carbon halogen bond depending upon the type of halogen. Okay. So, and then we talked about the methods of preparation of haloalkanes, and we started the first method, which was using the alcohols. Also, it contained three different categories. There were three subcategories in the alcohols method. One was using halogen acids. Then the second one was using the phosphorus halides, and the third one was using the thionyl chloride. Then we discussed the second method using the alkenes. The third one using the alkenes, and we also discussed in detail about the Markovnikov's rule. And then the last method was using the halogen exchange, in which we studied the two special named reaction, that was the Finkelstein reaction and the Schwarz reaction. Now, we also talked that these methods, they were not applicable for the haloarenes. So today we are going to discuss about the preparation of haloarenes. So we are starting with the preparation of haloarenes. So in this, we will only study the two methods. That is, the first one is from the hydrocarbons, and the second one is a special reaction, which is known as the Sandmeyer's reaction, and it uses amines. Okay. So the first method, that is the preparation of haloarenes from the hydrocarbons, it is based on the electrophilic substitution. And this method, it requires the presence of the Lewis acid catalysts like iron or iron chloride, that is Fe or FeCl3. So this thing is special, and it is this reaction has to be done in dark, that is no sunlight and all is used. So I am first writing down the reaction. This is benzene. Sorry, this is toluene. Then this is the halogen. This is iron, that is the Lewis acid that I just told you. And it is done in dark. And the results that what we get are the halogen is attached here. It has replaced one hydrogen that was already here. It has replaced that hydrogen. And the second one that you get here is, this is the first one is the ortho derivative, and the second one is the para. So here, this is the halogen. Okay. So the first one, this one is known as the ortho derivative. Like it will be known as ortho halotoluene, because this thing is toluene. And if suppose this X is the chlorine, this is X halogen is the chlorine one, then it will known as orthochlorotoluene. And this one will be called as para-chlorotoluene. Okay. So ortho means, why are we writing ortho? Because CH3 is attached here, no? So we will call it, this carbon, we will call it as one carbon. This will be 2 carbon. This will be 3 carbon. This will be number 4 carbon. Okay. And so on. So ortho is when two categories or two substituents, they are attached, two species, they are attached to the benzene ring in the adjacent position. That is 1 and 2. Meta. We call it meta when the two substituents, they are attached in 1 and 3, and we call it as para when the two substituents they are attached in the 1 and 4 positions. That is the opposite, just opposite position. So here you can see. Now this reaction, like because we are getting the two products, so you must be thinking that they need to be separated. But because ortho and para isomers, they have large difference in their melting points. So this mixture is easily separable. I mean, you can use the simple method for separating it because of their large difference in the melting points. Also, this X is only applicable. This reaction is only applicable for chlorine and bromine. This X will either be equal to chlorine or bromine. It is not for fluorine and iodine. Okay. Then reactions with iodine, they are reversible. So an oxidizing agent has to be used. So यहाँ पे if with iron we need to use some oxidizing agent, only then can we use. Only then can we obtain the product using iodine, the iodide. So for iodine, for X is equals to iodine, we need to use the strong oxidizing agents. Otherwise, the reaction will be reversible and we will not be able to get any product. Or you can say a very less yield of product. Now, X should not be equal to F2, that is fluorine. Why? Because of its high reactivity. Because fluorine is highly reactive. So this reaction is not applicable for fluorine at all in any condition. Okay. So now again one question may arise that because here we have discussed that ortho, meta and para, these three possibilities are there, right? But I have not written the meta product over here. So you may ask the question like why I have not included the meta product over here. So the reason for this is as the benzene rings, they undergo resonance, right? Resonance is the electrons, they are always, electrons, they are not at one position. They are just being traveling all around the ring. So that is resonance. You must have studied it in class 11th. So benzene has resonance in the ring. So because of this resonance thing, you will be able to understand that in the benzene, the electron density is high in this ortho position and the para position, and electron density is less in the meta position. Okay. So like in this compound, if we talk about, the electron density is high on the second carbon and on the fourth carbon, and then again on the sixth carbon, this sixth carbon. So electron density is high here, and these halogens, they are the electrophilic substances. These halogens are the electrophilic, मतलब electron loving species. So electron loving species जो होती हैं, they prefer to get attached at the more electron density वाले positions पे. तो जहाँ पे electron ज़्यादा मिलेंगे उन्हें, so they'll prefer to go at that position, attach at that position. So इसी वजह से these halogens, they prefer to get attached in the position number 2 and 4, that is the ortho and para. और मेटा पोजीशन पे बहुत ही कम इलेक्ट्रॉन डेंसिटी की वजह से we will not get any product. So we are not writing it here because even if some meta species is formed, it is very, very less in amount. So we don't count it over here. Okay. So I'm just writing the reason over here, like electron density is high at ortho and para position. Fine. So this was everything about the electrophilic substitution, like that is the preparation of haloarenes using the hydrocarbon. Now the second method is using the amines, and this is a special reaction which is known as a Sandmeier's reaction. Sandmeier's reaction. Okay, and it uses amines as a reactant. So what we do here is first let me write down the reaction and then I'll explain you the mechanism. So this is amine. This is known as aniline, like the complete compound. This comes with the benzene ring is known as aniline plus NaNO2. This is sodium nitrite. This is the acid at room temperatures. Right? And this compound is known as benzene diazonium halide, depending upon which halogen. If X is Cl, then we will call it as benzene diazonium chloride. Okay. So this is the first step of this reaction, of the Sandmeier's reaction. So what we do here is that amine is dissolved in a acid. This acid is HXO. So it is dissolved in a mineral acid and then it is treated with sodium nitrite. And the product that we are getting is a diazonium salt. Okay. But this is only the first step because still we have not got the haloarene. So what we do is the second step here is the first step is common for chlorine, bromine, and iodine. But the second step is different for these species. So this is step number A. And step number B for X, which is chlorine and bromine. The second step will be it is treated with cuprous halide. And we get the nitrogen gas. So this is for the chlorine and bromine. The special thing is that in the second step, there is a presence of cuprous halide is required. And we get this reaction. And similarly, for X is equals to I, that is for the iodine, we can simply shake this salt. This is the diazonium salt in the presence of potassium iodide. So we will get for iodine, because हमें iodine का compound चाहिए और ऊपर हमें chlorine और bromine के लिए यहाँ पे CO2. If we want chloride, then we will write CO2Cl2, and if for bromine, we will write Cu2Br2. Simply for the iodide, we will use Ki, and we will get the iodide over here. So this is our haloarene. Okay. So these are the two steps. The first one is A and the second one is B. So this is the complete Sandmeier's reaction. Now these were the two methods for the preparation of haloarenes. Now I would like to do some examples, and then we will move on to the physical properties. Okay. So the first example, this is a benzene ring. And this is the alkene plus HBr. And what will be the product? So this we have done in the previous lecture, that when we are reacting any alkene with the halogen acid, then what the product would be like this. This will break into H plus and Br minus, and this H plus and Br minus will try to remove this unsaturation, and it will get attached to, like the H will get attached to one carbon, and the bromine will get bromide ion will get attached to the carbon, other carbon that is a part of the double bond. Okay. But you must also remember here the Markovnikov's rule that we discussed. So you just have to apply the Markovnikov's rule over here and write the major product. So again, I am just making you remember the Markovnikov's rule, that it says that the hydrogen will get attached to the carbon which has more number of hydrogen, and the halide ion will get attached to the carbon with the less number of hydrogen atoms. Okay. So let's count the number of hydrogen atoms over here. So this carbon we have two double bonds, and so this carbon will have two hydrogens, right? 2H. And this carbon, the carbon number 1 will have two hydrogens, and this carbon number 2 will have, because there are 3 bonds, it will have only one hydrogen. Okay. So according to the Markovnikov's rule, the first carbon will add up the hydrogen. The hydrogen will get attached to the first carbon and bromine to the second carbon. So now our product will look like, this is the ring, double bond has disappeared because now unsaturation is not there. The compound has been saturated. So this is Br. So the hydrogen will get attached to the first carbon. Fine. Now the second thing is, now this one is also similar. This one also you will have to apply the Markovnikov's rule. So again, when we are counting, so this carbon will have one hydrogen and this carbon has two hydrogen. Fine. So again, the compound will look like, Cl will be here and here it will be CH2. Okay. Now the next example is a little tricky. This is also an alkene here, alkene group plus HBr. But here we are doing the reaction in the presence of peroxide. Okay. So the trick here is that you will have to remember this. This is an important note. Okay, so you will have to just highlight this, that whenever this reaction is being done in the presence of the peroxide, the Markovnikov's rule will not apply over here. Or you can see that the Markovnikov's rule gets reversed. I mean, the conditions, the two conditions of the Markovnikov's rule will get opposite, and it will get reversed in this case. So in the presence of peroxide, what you get is कि जो hydrogen होगा will attach to the carbon with less hydrogen, and halogen will get attached to the carbon with more hydrogen. I mean, it's just the opposite, but you'll have to remember. So now the product here will look like CH2, CH2, CH2 and Br. So यहाँ पे जो halogen है, that is getting attached to the last or the first carbon. ठीक है? So this was the examples. These were the examples related to the Markovnikov's rule. And now we will move on to the physical properties. Okay. So the first physical property that we will discuss is the color and the odor. ठीक है, of these compounds. So talking about the color and the odor, generally alkyl halides, they are colorless if they are taken in the pure form. So the color is colorless, but the bromides and iodides, they develop color when they are exposed to light. So this is a special condition that when they are exposed to light, the bromides and the iodides, they will develop some kind of color, light color. Talking about the odor, many of these compounds, they are sweet smell. But obviously these things, these two properties, they are not very relevant, relevant when we talk about the chemical reactions. But coming to the next one, we have melting and the boiling point. So the special thing about the state of these compounds is that methyl chloride, methyl bromide, that is methyl chloride, then methyl bromide, then ethyl chloride, and some of the chlorofluoromethanes, they are gases at the room temperature. ठीक है, ये है, these are all gases at room temperature. But at the higher alkyl halides, they are all liquids or solid. ठीक है, so we are talking about the melting and the boiling point of those liquids and the solid things. ठीक है, so here how will we study how, like, we'll compare the melting and the boiling points of the haloalkanes with the different materials, and then we'll analyze that how are they increasing or decreasing. Okay, so when we talk about the, like, when we compare these with the parent hydrocarbon मतलब जैसे ये methyl chloride है, तो इसका parent hydrocarbon हो गया मीथेन, that is CH4, क्योंकि वो उसी से बना हुआ है, CH4 से. ठीक है, if we are talking about this C2H5Cl, its parent hydrocarbon will be ethane, that is C2H6. ठीक है, so see, we discussed in the previous lecture that the halides, they develop polarity, that is the separation of charges because of their electronegative character. Okay, because of the electronegative character of the halogens. Also, they have more molecular mass. So obviously, like CH3Cl will have more molecular mass as compared to CH4 because chlorine is added in CH3Cl. Okay. So because of these two things, the intermolecular forces of attraction, they are stronger in the alkyl halides. So because जब ज़्यादा polarity होता है और ज़्यादा molecular mass होता है, तो जो in forces of attraction होते हैं वो भी ज़्यादा होते हैं. And which kind of forces we are talking about here? दो, क्योंकि polarity है तो इस वजह से dipole interaction होगा. Dipole interaction क्या होता है? Let me tell you. When we discuss that CX bond has polarity, that means it has partial positive and the halogen has partial negative charge. ठीक है, तो जब यहाँ पे चार्ज आ जाता है तो हम लोग इनके बीच का जो इंटरेक्शन होता है बिकॉज ऑफ दीज पार्शियल चार्जेस, इट इज नोन एज द डाइपोल इंटरेक्शन. ठीक है, और जो वॉन डर वाल्स फोर्सेस होते हैं, these they are also very weak kind of forces of attraction. So these two forces are considered here. So yeah, so that means that the forces of attraction are more in the case of alkyl halides. ठीक है, इसी वजह से जो halides होते हैं, they have more boiling points as compared to the parent hydrocarbon. So the conclusion says that alkyl halides have more boiling point. This BP is for boiling point than their parent hydrocarbon. ठीक है, and why is this so? because of more polarity and more molecular mass. Both these things, they result in stronger interaction. Okay. So this was the comparison on the basis, like comparison with the parent hydrocarbon. Then we compare the boiling points among the different halides. मतलब जैसे अगर हमने alkyl group को same रखा, same मतलब we have taken it, suppose it's propane, ठीक है, so we'll talk about the propyl group over here. ठीक है, अब हम propyl, ठीक है, तो different halide. We're talking about the propyl group. Let's suppose, ठीक है, so propyl iodide, propyl bromide, propyl chloride, and propyl fluoride. I mean, what would be the trend or what would be the order of the boiling point? So again, as we discussed, the increase in the molecular mass and the size of the halogen atom, it will increase the van der Waals forces of attraction. ठीक है, अभी पीछे हमने ये चीज डिस्कस किया. ठीक है, तो the same reason here, यहाँ पे क्या होगा, क्योंकि हमारा alkyl group तो same है, the only change is in the halogen. ठीक है, तो फ्लोरीन सबसे छोटा होता है, उसका मास सबसे कम होता है, and then we'll go on to chlorine, then bromine, and then iodine. So that means तो हमारा alkyl iodide होगा ना, it will have the maximum van der Waals force, and so it will have the maximum boiling point. Just writing the trend, the reason will be the similar one as in the previous case. R here is for any alkyl group. ठीक है, तो यहाँ पे कंपेयर करते टाइम हमने R को कॉमन रखा है, बिकॉज अगर R चेंज हो गया तो फिर देन वी नीड टू टेक इनटू अकाउंट द मास ऑफ R ऑल्सो. ठीक है, R है, fluoride is least boiling point. Now, like if we keep the molecular mass same, लेकिन हम ब्रांचिंग बढ़ा देते हैं. अभी हमने मोलिकुलर मास चेंज किया तो ऐसा ट्रेंड आया. अब हमने क्या करा है कि हमने जो हमारा मतलब मोलिकुलर मास है, और यू कैन से द नंबर ऑफ कार्बन एटम्स एंड नंबर ऑफ हाइड्रोजन एटम्स, दे आर सेम. मोलिकुलर मास हमने सेम रखा, बट वी आर टेकिंग द डिफरेंट आइसोमर्स. ठीक है, तो कैसा ट्रेंड रहता है बॉइलिंग पॉइंट में? So it has been observed that the boiling point, it decreases with the increase in branching. मतलब कि जैसे सपोज करो अगर हमारा नॉर्मल वाला लेते हैं with the 4 कार्बन एटम्स, और फिर हम लोग एक इसका आइसोमर लेते हैं जिसमें हम एक ब्रांचिंग कर देंगे. चेन हमारी वैसे ही है, ब्रांचिंग हमने किसकी कर दी है? ब्रोमीन की. ब्रोमीन को इधर पे लगा दिया साइड चेन की तरफ. नाउ हम लोग इसका आइसोमर ले रहे हैं, ये एक ब्रांचिंग हमने मिथाइल ग्रुप की भी कर दी है. बट सी द नंबर ऑफ कार्बन एटम्स हियर आर ऑल सेम. I mean everything. Bromine is also single bromine everywhere. तो इसका मॉलिकुलर मास जो है इन सबका वो ऑलमोस्ट सेम है. बट इसका जो ट्रेंड है बॉइलिंग पॉइंट का, दिस इज ऑब्जर्व्ड इन दिस वे, क्योंकि यहाँ पे ब्रांचिंग ज्यादा है तो ऑलरेडी कुछ इलेक्ट्रॉनिक रिपल्शन होंगे, क्योंकि अगर चीजें जो होगी, अगर हमारे जो ग्रुप्स हैं या फिर जो सब्स्टिट्यूएंट्स हैं वो बहुत पास पास लगे हुए हैं. ठीक है, इन दिस केस है काफी ज्यादा, बिकॉज जो कार्बन एटम है और हाइड्रोजन एटम भी, एक कार्बन पे 3 हाइड्रोजन लगे हुए हैं एवरीवेयर. ठीक है, तो ऑलरेडी इतना ज्यादा क्राउडेड होगा, जो कि इतना पास पास इलेक्ट्रॉन क्लाउड्स होगा कि थोड़ा बहुत इलेक्ट्रॉनिक रिपल्शन भी आएंगे. एंड बिकॉज ऑफ दिस क्लोजनेस, बिकॉज ऑफ दीज इलेक्ट्रॉनिक रिपल्शन, तो जो इंटरेक्शन होंगे ना वो थोड़े बहुत वीक हो जाएंगे. ठीक है, तो जितने स्ट्रॉन्गर इंटरेक्शन होंगे उतना ज्यादा बॉइलिंग पॉइंट होगा, और जितने वीक इंटरेक्शन होंगे उतना बॉइलिंग पॉइंट कम होगा. तो इस वजह से ब्रांचिंग की वजह से जो बॉइलिंग पॉइंट होता है इट रिड्यूसेस. ठीक है, नाउ another point you need to remember here is that the boiling point of the isomeric dihalobenzenes are nearly or approximately they are same. Dihalobenzene is like we just seen, no, when bromine is added, like one benzene is when one benzene ring is there and two halogen atoms are attached. ठीक है, तो उनके जो आइसोमेरिक डाइहालोबेंजीन्स होते हैं, दे आर नियरली द सेम बॉइलिंग पॉइंट. So I'm talking about this. This is the ortho one. Then this is the meta. These are all isomers. इनको आइसोमेरिक बोलते हैं क्योंकि मॉलिक्यूलर मास तो कम्प्लीटली सेम है, नंबर एंड द टाइप ऑफ एटम भी कम्प्लीटली सिमिलर है. बस डिफरेंस क्या है कि जो सीएल का पोजीशन है लगने का वो डिफरेंट है. तो दिस इज अ पैरा. ठीक है, इनका जो बॉइलिंग पॉइंट होगा, बॉइलिंग पॉइंट होते हैं वो सेम होते हैं नियरली, बट यहाँ पे अंतर का डिफरेंस आता है इन द केस ऑफ मेल्टिंग पॉइंट. ठीक है, तो इट हैज बीन ऑब्जर्व्ड दैट मेल्टिंग पॉइंट ऑफ द ऑर्थो एंड मेटा आइसोमर्स इट इज नियरली सेम. मतलब अगर हम इनको कंपेयर करें तो ये ऑर्थो ये मेटा, इट इज नियरली सेम, मतलब ऑलमोस्ट इक्वल होता है, थोड़ा बहुत डिफरेंस. बट दिस पैरा आइसोमर इट हैज अ लार्ज मेल्टिंग पॉइंट. तो इसका मेल्टिंग पॉइंट बहुत ज्यादा होता है एज कम्पेयर टू द अदर वन. और ऐसा इसलिए होता है बिकॉज दिस पैरा आइसोमर इज सिमेट्रिक. एज यू कैन सी, मतलब अगर यहाँ पे अगर लाइन आप ड्रॉ करो ऐसे, तो ये बिल्कुल सिमेट्रिक मॉलिक्यूल है. ऐसे भी ड्रॉ करो तो भी बिल्कुल सिमेट्रिक मॉलिक्यूल है. ठीक है, तो दोनों तरफ से इट्स अ वेरी सिमेट्रिक मॉलिक्यूल. एंड सो ये जो पैरा आइसोमर्स होते हैं वो बहुत ज्यादा स्टेबल होते हैं. इस वजह से उसको उसका बॉइलिंग पॉइंट ज्यादा होता है, उसे ज्यादा टेम्परेचर चाहिए होता है to get into the gaseous form. So just remember this thing, that symmetric things are always more stable. Symmetric things are always stable as compared to the non-symmetric or the anti-symmetric things. Okay. Now we come to the another physical property, which is density. Now bromides, iodides and the polychlorides, they are heavier than water. क्योंकि उनकी डेंसिटी मेजर करी गई एंड इट इज बीइंग कंपेयर्ड विद वाटर. दैट इज वाटर की डेंसिटी इज 1 ग्राम पर ml और 1 ग्राम पर सेंटीमीटर क्यूब. ठीक है, तो उसके कंपैरिजन में इफ वी सी, लेट मी राइट इट डाउन, ब्रोमाइड्स, आयोडाइड्स और पॉलीक्लोराइड. मतलब इसमें क्लोराइड इंक्लूडेड नहीं है बिकॉज इट हैज बीन ऑब्जर्व्ड दैट जो सिंगल क्लोराइड्स होते हैं, मतलब मोनोक्लोराइड्स होते हैं, उनका डेंसिटी इज लेस देन द डेंसिटी ऑफ वाटर. लेकिन पॉलीक्लोराइड्स के केस में इट इज, इन सब की जो डेंसिटी होती है इट इज मोर एज कंपेयर टू वाटर विच इज 1 ग्राम पर ml. ठीक है, नाउ जो डेंसिटी का ट्रेंड होता है चेंज होने का, दैट इज इट इंक्रीजेस with the increase in the number of carbon atoms or halogen atoms or the mass of halogen atom. ठीक है, तो density increases कब होगा? when number of carbon atoms जो होंगे वो बढ़ेंगे, नंबर ऑफ हैलोजन एटम्स होंगे वो बढ़ेंगे, तो मास बढ़ जाएगा. बढ़ेंगे तो भी डेंसिटी बढ़ेगा, और मास ऑफ हैलोजन मतलब FCl-Br(I) इस ऑर्डर में ये बढ़ेगा. तो डेंसिटी का ट्रेंड ये रहता है. ठीक है, नाउ वी कम टू द last physical property, that is solubility. So haloalkanes are slightly soluble in water, very slightly. I mean, we can even neglect them. And when we compare their solubility with water and the other organic solvents, it's negligible in the case of water. And why is it so? Because the original hydrogen bonds in water, they are stronger than the new attractions between the water and the haloalkane molecule. मतलब सिंपल वर्ड्स में बोले तो जब हेलो एल्केन्स मतलब जब आपस में हेलो एल्केन्स का जो बॉन्डिंग होता है वो काफी ज्यादा स्ट्रांग होता है, उनका जो अट्रैक्शन होता है वो इंटरेक्शन होता है वो ज्यादा होता है। और जब हम हेलो एल्केन्स को वाटर के साथ मिलाते हैं, व्हेन वी डिसॉल्व दीज हेलो एल्केन्स विद वाटर, तब जो अट्रैक्शंस होते हैं या फिर इंटरेक्शंस होते हैं वो वीकर होते हैं। और बिकॉज ऑफ दीज वीकर इंटरेक्शंस जब फोर्सेस ही नहीं होंगे तो एनर्जी रिलीज नहीं होगी। तो इसका मतलब है कि वेरी लिटिल अमाउंट, लेस अमाउंट ऑफ एनर्जी इज रिलीज्ड, और इसी वजह से हैलोअल्केन्स आर वेरी स्लाइटली सॉल्युबल इन वाटर। Solubility in water is very less. Okay, and if we talk about the solubility in the organic solvents, तो दे आर soluble in organic solvents, क्योंकि रीजन सेम है कि जो न्यू इंटरमोलिकुलर इंटरेक्शंस they are present in the solution of haloalkanes and organic solvent। तो उस सोल्यूशन में जो इंटरमोलिकुलर इंटरेक्शंस हैं वो सिमिलर स्ट्रेंथ के होते हैं, मतलब ना वीक होते हैं ज्यादा और ना ज्यादा स्ट्रांग होते हैं, तो सिमिलर स्ट्रेंथ के होते हैं एज कंपेयर टू द जो प्रीवियस उनके हैलोअल्केन के अपने खुद में इंटरेक्शन थे। ठीक है, तो सिमिलर इंटरेक्शन ही होते हैं, तो इस वजह से वो लोग सॉल्युबल होते हैं। So this was all about the physical properties. We discussed 4 physical properties. That was the color and odor. Then the second one were the melting point and the boiling point. Then the density and the solubility. Okay. Now our next topic would be the reactions, like which chemical reactions they are being carried out यूजिंग दीज हैलोअल्केन्स एंड हैलोएरीन्स। पहले हमने क्या पढ़ा था कि वो लोग बनते कैसे, लाइक हाउ दे आर प्रिपेयर्ड, हाउ आर दे मैन्युफैक्चर्ड यूजिंग द डिफरेंट कंपाउंड्स। अभी वील सी विच काइंड ऑफ केमिकल रिएक्शंस दे आर बीइंग डन यूजिंग दीज कंपाउंड्स। ठीक है, तो इससे हमें उनकी एप्लीकेशंस के बारे में भी पता चलेगा कि कौन कौन से इंडस्ट्रीज में वो यूज होते हैं। तो वी विल कंटिन्यू दिस टॉपिक इन द नेक्स्ट लेक्चर। So this was all for today. Thank you.